Hello, this is Tyler Beamer from Haywood Community College. This is an instructional math video for Math 152 IN1. The purpose of this video is to go through an example using central limit theorem, and this is chapter 6, section 5 of our textbook. Here is the example that we're going to use. Before every flight, the pilot must verify that the total weight of the load is less than the maximum allowable load for the aircraft. The Bombardier Dash aircraft can carry 37 passengers, and the flight has fuel and baggage that allows for a total passenger load of 6,200 pounds. The pilot sees that the plane is full and all passengers are men. The aircraft will be overloaded if the mean weight of the passengers is greater than 6,200 pounds divided by 37, which is 167.6 pounds. What is the probability that the aircraft is overloaded? Should the pilot take any action to correct for an overloaded aircraft? Assume the weights of men are normally distributed with a mean of 182.9 pounds and a standard deviation of 40.8. Okay, so what I want to first do is find the probability using normal distribution that one randomly selected man is over 167.6 pounds. If we randomly select one man from the population, what's the probability that their weight is greater than 167.6 pounds? Okay, so we can use normal distribution because it gives us this information here that weights of men are normally distributed with a mean of 182.9 pounds and a standard deviation of 40.8 pounds. Okay, so this is essentially what you guys practiced in section 3 when you were using normal distribution and solving applied problems. Okay, so I wanted to start with this just to kind of give a refresher, and then we'll go into actually solving the problem using the central limit theorem. So obviously this is not standardized. Our mean is not 0 and our standard deviation is not 1. So because of that, we need to use the z-score, which looks like this. Okay, and the z-score standardizes our data and it basically tells us how many standard deviations away from the mean we are. Okay, so we would want to plug in our value for x, which in this case is going to be 167.6 pounds. Subtract that from our mean, 182.9, and divide that by our standard deviation, 40.8. Okay. And if we calculate that, we get a z-score of negative 0.375. Our z-score is negative here because our data value of 167.6 is less than our mean of 182.9. Okay, so if we look at this graphically, right, we've got our normal curve, we've got our mean in the middle, and our data value is less than the mean, and we want to find the probability that one randomly selected person is greater than 167.6 pounds. So we want to find to the right of that data point on our curve. So in order to do that, we would take the entire curve, so everything, right? So every possible weight value, and all those probabilities summed is 1, minus the probability that it is or one randomly selected person is less than 167.6 pounds. Okay, and we can come up with this probability from our z-table using our z-score. Okay, so if we look at our negative z-table, okay, we want to find negative 0.375, and of course our z-score only goes to the hundredths place, so we're going to round that to negative 0.38. Okay, so remember we find the tenths place on the column here to the left. So here's negative 0.3, and then we would find the hundredths place up here at the top, 0.8. So negative 3.8 is going to be where those two combine together, which is going to be at 0.3520. Okay. So that tells us that there is a 0.3520, or roughly 35% chance of randomly selecting someone less than 167.6 pounds. However, we want the probability that it's greater than 167.6 pounds. So we want to subtract that from 1. Okay, and when we do that, we get 0.648. So there's roughly a 65% chance that if we selected one randomly selected man from the population, that they're going to weigh more than 167.6 pounds. Okay. And then the 167.6 pounds, remember, is the maximum mean weight of each passenger that there could be before the aircraft is overloaded. Right? The aircraft can hold 6,200 pounds. It can hold 37 passengers. So if you divide those two numbers, you get 167.6. So if every single person on the plane weighs 167.6 pounds, then the aircraft would be at capacity. Okay, and then there is a 64.8% chance that if we select any random man from the population, that they're going to weigh more than 167.6 pounds. So just keep that in mind. Okay. Alright, so what we're really after is the probability that the plane's overloaded. So obviously there's not just one person flying on the plane, right? There's 37 people flying on the plane. So this is where the central limit theorem comes into play, because our sample is greater than 1. Okay, and the central limit theorem states that if we have a sample size that is greater than 30, okay, then the sample could be approximated using the normal distribution. Okay, essentially the greater n gets, so the larger the sample size, okay, the more closely that distribution models the normal distribution. Okay. And the mean of all of the sample means approaches the population mean. Okay. And in our case, we do have a sample size greater than 30, so we could employ the central limit theorem here. But since we are taking from a population that is normally distributed, okay, then we could then also still use the normal distribution. Okay, so either way we're covered in this particular problem. Okay. Alright, so find the probability that 37 randomly selected men have a mean weight greater than 167.6 pounds. Okay, so let's slide this up. Our mean from our problem is still 182.9. Okay. But since our sample is greater than 1 and it's 37, right, we need to employ the central limit theorem, okay, which states that we need to take our standard deviation, 40.8, and divide that by the square root of n, and n is the number of people in our sample, which in this case is 37. Okay. And when we compute that, we get 6.7074. Okay. So because we are using or finding the probability of 37 randomly selected men, right, we need to change our standard deviation to reflect the central limit theorem. Okay. So we're thinking about this in context. We're trying to find the probability that if we select 37 random men, that the mean weight of those 37 men is greater than 167.6 pounds. Okay. So once again, we've got our mean, we've got our standard deviation. This is also not standardized, right? I mean, our mean is not 0, standard deviation is not 1. So once again, we use our z-score. Okay, we're still using 167.6 as our value of x, and still have the same mean. The difference is our standard deviation has changed because our sample is 37, not 1. Okay, so now when we compute that z-score, we get negative 2.28. Okay. So notice that we're further away from the mean. Okay. Our standard deviation is much different than when we were selecting one person. So let's look at that graphically. So once again, we're trying to find the probability that a random selection of 37 men yield a mean weight greater than 167.6 pounds. So we want to the right of that. So we use the same methods here. We take the probability, all probabilities, which would be 1, so everything under the curve, and minus less than 167.6, and that gives us what we are looking for, right? So we need to find the probability that if we select 37 randomly selected men, that their mean weight is going to be less than 167.6 pounds. Okay, so we use our z-score to do that. Once again, it's still negative. So we want to find negative 2.28. So here's negative 2.2. And here is the 8. So we look where those line up. And then it's right here. Okay, so 0.0113. Okay, so that is the probability, or the area underneath this curve here, 0.113. Okay, so then if I subtract those, one minus 0.0 113. I get 0.9887. Okay. So then that tells me that there is a 98.87% chance that if I randomly select 37 men from the population, that their mean weight is going to be over 167.6 pounds. So that is a really good probability, really good chance that that aircraft is going to be overloaded. Okay, and that makes sense. I mean, if we look at what we did to begin with, we found that the probability of selecting one man out of the population and that one man weighing more than 167.6 pounds was 64.8%, which was pretty good. That's definitely more than half chance that you're going to get somebody weighing over that. So if you select 37 people, 37 men, right, then that probability that their mean weight is greater than 167.6 pounds should be pretty good. I mean, that should be really good chances there, and it is, right? 98.87% chance that they mean weight will exceed 167.6 pounds. And we're selecting more people. Therefore, this pilot should definitely take some action here to try to correct the air load or the overload of the aircraft. They could release some fuel, some baggage, take fewer passengers, so on and so forth. Okay, but the statistics allows us to make a good judgment call there, so that no one is put at risk. So I hope that this example helps. We're employing a lot of the same tactics here for solving these normal distribution problems. The difference in this section is that we are not only just selecting a single person, but we're selecting more than that. So therefore, we've got to make this adjustment in our standard deviation here, dividing that by the square root of n. That's the main difference. Okay. My door is always open. If you have any questions, or email me. I hope this video helps. At least gives you another example video tutorial to help you with those problems.